السلام عليكم ورحمة الله وبركاته. أهلا بحضراتكم، معكم الدكتورة آية نصار من قسم الفيزياء الحيوية، ويسعدني اليوم أن أشارك معكم في ورشة العمل لنستطلع أحد أهم الموضوعات عن تحليل البيانات في مجالات العلوم البيوفيزيائية. There are three main objectives for this session: to gain experience with data analytic tools, to understand and apply fundamental data analytic techniques to datasets that are relevant to molecular biophysics, as well as to develop the ability to integrate data analytics and visualization outcomes so you can support innovative solutions in research. Through this session, I will guide you through the current trends in modern sciences. We will highlight the significance of using data-driven research, provide an overview of the basic data analytics and the visual tools, and ultimately summarize the significance of integrating data in current health innovations. Start with, we need to look at the current trends in modern medicine. I would like to emphasize the role of biophysics in various forms of interdisciplinary research. Molecular biophysics provides the fundamental knowledge and the tools that drive innovations in medicine and health, leading to better diagnostics, treatments, and overall health improvement. If we look at the connections between biophysics and medicine, we see that insights from molecular biophysics are crucial for medical achievements. For example, understanding the structure of the protein, the DNA, that led to the development of targeted therapies for diseases, for example, cancer and genetic disorders. So techniques from biophysics, they can be used in medical imaging, and one of these diagnostic tools, such as the magnetic resonance imaging. When we look at the connections between biophysics and health, we find that the knowledge gained from molecular biophysics, it helps in understanding the molecular basis of diseases, which is essential for developing effective treatments and consequently preventive measures. For example, studying the molecular mechanism of neurodegenerative diseases, it can lead to new therapeutic strategies. With the current innovations in bioinformatics, molecular biophysics provides both the experimental and the theoretical framework, making these computational tools essential for analyzing and interpreting data, thereby establishing them as interconnected disciplines in life sciences at the molecular level. There are currently several exciting trends that are shaping the field of biophysics, especially in data analytics. One of them is the big data and the deep sequencing. This approach has been allowing comprehensive exploration of genomes. It enables discovery of novel biomarkers. And if we look at the machine learning and the current AI, those models, they help in predicting some molecular interactions as well as biological processes and the mechanism. We look at the omics data, so the integration of multi-sources, combining data from genomes that can help identify some complex systems interaction and identify the pathways. For example, we can look at the current innovations in nanotechnology. Some of it is based on AI driven solution. So you can come up with some diagnosis for cardiovascular and respiratory disorders. There are current tools and techniques that are highly in demand for research, including data analysis, modeling, and simulation. Let's explore the use of some data in research and innovation. Using data in computational analysis, it guides innovations in new drug designs, identification of targeted sites, understanding mechanisms of action and interactions, as well as predicting molecular structure. Achieving these innovations is made possible through big data collaboration, utilizing machine learning to identify phenotypes and early predictors, enhancing prognosis and targeted treatments with statistical analysis, in refining drug design and effectively through computational modeling. Harnessing data driven decisions is transforming research and development, driving efficiency, reducing cost, and paving the way for personalized and more effective healthcare solutions. This takes us to one of the most prevalent research topics, which is personalized medicine. Personalized or precision medicine is one of the new approach in tailoring the treatment for patients. This takes into account different factors such as the genetic, the environmental, and the lifestyle of the patient. So those kind of treatments are specifically designed to fit the unique molecular profile for the patients. So there is a connection between biophysics and precision medicine, in which biophysics plays a major role to give some insights about the molecular mechanism that underline the disease development and how can different treatments be tailored for different patients by addressing the molecular structure and understand the process at the atomic level. As a researcher, your research journey might involve some experimental approach where you design your own experiment, you collect the data. So this is primary your own data source. There's another way of accessing data through some data hubs or some shared data. And this is where you play a role in analyzing the data and trying to come up with some information about what you present. In your journey as a researcher, you want to ensure that your research is a data driven research and it's based on evidence. Evidence based research is a systematic approach that relies on evidence that's gathered from different methodologies like randomized clinical trials, observational studies, and through doing a meta analysis. It aims to provide reliable and valid results that can be replicated by other researchers and it can be later generalized to broader population. There are key components for evidence based research that would include systematic reviews where you can look at relevant studies and come up with a summary for what has been concluded. As well, there is a meta analysis in which you can combine different data from different studies and sources and come up with a broader conclusion. As well, in medicine, this can be applied by using what is called randomized controlled trial in which you can try the treatment on different patients and see the efficacy for each treatment. Reading and critically appraising published research studies is very important for professionals who intend to make evidence based decisions. Make sure when you review articles that you have answers for the big four questions: the why, the how, the what, and the so what. Keep those questions in mind when you look at peer review articles. You want to make sure that the research in hand has a clear hypothesis. There is a research question that the author has intended to answer. There are some meaning insights that they can take out of the results. Understanding the method is important before you attempt to analyze the data. Let's quickly review the research process. There should be a topic where you would like to address. You would develop your research question. You will set your hypothesis. You will come to the analysis. Then you will draw your conclusion and come up with some inference. Let's see the best way so you can formulate your research question. In your question, you want to make sure to identify a topic through a comprehensive literature review. You want to narrow down your research results. Then you need to identify the gaps between your findings and what new that you would like to apply. Then you can narrow down your question until you identify your variables. Next step is to set your objectives and identify the type of the analytic question. There are a few different approaches that you can set in mind when you come to your question. You might be interested in describing an event by giving a summary of the variables and the factors that you have. You might also want to analyze more deeply and compare between the factors and then come up with kind of association or a relationship. In cancer research, for example, we are interested in survival time, so we look at the event over the time, as well in simulation and modeling. We would like to come up with some predictive structure, for example. Descriptive questions focus on summarizing and describing an event, such as the protein stability. For example, you would provide some summary of the structure, some parameters, and look at the trends and the variation on those complexes. Analytical questions involve examining the relationship between two variables. In such analysis, you will be able to look at regression or correlation analysis to determine the strength and the significance of the association. Comparative questions can involve comparing the effectiveness of two drugs or two treatments. In this case, a t-test or an ANOVA can be used to determine if there is a significant difference between the two treatments. In longitudinal analysis questions, those are intended to explore the change over time. For example, looking at the survival rates for a treatment at early stage and late stage for cancer. For predictive questions, those are intended to develop a model that can be used in a biological system using data that can predict how well the patient can respond to a specific treatment. When stating your question, you want to make sure that your question does not have an obvious answer and it requires further research. It allows you to explore more in depth for different tools and different alternatives, as well as it will allow you to use different data sources and you can move forward with your research. Let's have a look at this type of the question. How does breast cancer develop? Would you agree that this is a good question? It's a bad question, or you're not sure? This question is kind of broad question and it's not specific. As you see, this question does not focus on the factors that will be investigated to come up with the conclusion. Alternatively, you can have a more specific question and focus in the area of the molecular research. For example, your research question can be stated as how do specific mutation in the breast cancer gene influence the structure and the stability of the protein and how its interaction with the DNA during the repair process. To be able to refine your research question, you might need to conduct more literature review, go specific and identify the key components for your investigation, eliminate any unnecessary details, then you can articulate the prevention or the strategy that you would like to proceed with, and then finally you can establish a time frame. Let's investigate this refined question. How do mutations in genes affect cancer development? Although this question seems to focus on mutation, it still needs to specify the type of the mutation and its relation to the protein. The modified question could be something like in breast cancer patients, how do the specific BRCA1 gene mutation affect the structural stability of the protein during the DNA repair? Next, let's go through the data cycle. In general, there are two types of variables. There is the independent variable that you can manipulate and change, and there is the dependent variable where you can measure, then you can look at the cause and the effect. Before you proceed with the analysis, you want to clearly state a hypothesis. We state a hypothesis to provide a clear, testable prediction that will guide your direction in the research. The null hypothesis states that there is no significant difference between the predictor and the outcome. In the case of the breast cancer gene, the statement will show that there is no significant difference between the mutated version and the non-mutated version when it comes to breast cancer. This table outlines the appropriate bivariate analysis that are commonly used in scientific research. Use the contingency table or the chi-square test to analyze the relationship between two categories. Use the group means, it's called t-test or one-way ANOVA test, to compare the means of continuous variables across different categories. You will use the correlation analysis or linear regression to assess the relationship between two continuous variables. We use logistic regression in terms of predicting the influence across the categorical outcomes. The strength of evidence against the null hypothesis is mainly based on the p-value that's obtained from the test. For example, when you set the p-value of zero point zero 0.05, this means that the evidence is moderate, and this is commonly accepted as a threshold in many scientific studies, suggesting that there is enough evidence to consider rejecting the null hypothesis. However, when the p-value is zero point 0.1, the evidence against the null is borderline, and there is some indication that the null hypothesis might not be true, but it's not strong. When the test statistics falls into the critical region, the observed result is considered statistically significant. This means that the evidence suggests rejecting the null hypothesis in favor of the alternative hypothesis. If the test statistics falls outside that critical region, the null hypothesis is not rejected, and this indicates that there is not enough evidence to support the alternative hypothesis. For example, imagine that you are conducting a one-tailed t-test at 0.05 significance level. The right tail of the distribution is the shaded area, is the critical region. If your test statistics lies in this area, it means that you reject the null hypothesis, suggesting that the effect or the difference you are testing is statistically significant. There are two types of error that you need to consider. A type 1 error that occurs when you reject the null hypothesis when it's actually true. And then you need to look at the significance level. The probability of making a type 1 error, you can denote this as the alpha level, and it's often said to be zero point zero 0.05. And this means that 5% chance is incorrectly rejecting the null hypothesis. The type 2 error, it occurs when you fail to reject the null hypothesis when it's actually false. And here you consider the power of the test, which we call it the 1 minus the beta. And this is the probability of making type 2 error. Next, let's have a look at different approaches. After getting your data, have in mind a few questions to brainstorm the analysis. For example, what is the most common between the variables you have? Is there a certain distribution? Is it normal or the data is skewed? Can you see any of the outliers? Do you need to have a visual for what you have? Or do you want to provide a summary statistics? In the scenario where the main purpose is to identify some of the risk factors that are related to a disease, you are looking for correlation analysis, regression models, or network analysis. An example of this approach is to analyze some of the clinical data to identify disease biomarkers. In this scenario, you can combine different sources of data, including clinical data, imaging, or omics data. Another scenario is to predict the patient outcome with the treatment so you can look at the efficacy of a treatment. The best approach is to use some statistical methods to analyze the time to event data. In this scenario, the best approach is to use survival analysis, and the common method is the Kaplan-Meier curve in the Cox proportional hazard model. The outcome for this is to improve the understanding of the treatment effects and to look at the survival time. Now, let's look at the tools that you can use for your analysis. Excel is one of the best tools that you can use for your analysis. It comes as a package with the Microsoft Office. In this version, you need to make sure that you activate the Data Analysis Tool Pack, which provide you with descriptive statistics. If you have this tool pack installed already, then you can use Data, go to Data Analysis, and then click on Descriptive Statistics. If you don't have it, you need to make sure that you go to Add-ins and then add this tool. If your plan is to start with providing a summary statistics of the variable and the factors you have, you can simply use the average and the standard deviation or any of the descriptive analysis to look through the data. The easy way is to click on Help and type the functions. The commonly used functions are provided in the tool pack. The way you do it is you select the range of the variables that you would like to consider. Let's consider this simple scenario. In this data set, I am providing you with some numbers, and I have provided the data dictionary so you can understand the codes. My aim is to evaluate the effectiveness of a certain treatment that has been administered to reduce the rate of a disease. And here I'm using two different types of treatment. I would like to compare between treatment 1 and treatment 2. It doesn't have to be a treatment, it can be a treatment and a placebo. Using Excel, at the top of the toolbar, go to Data and then choose Descriptive Statistics. When you click OK, it will give you a set of options. You will have a pop-up window that asking you to choose the input of the data range. You will click on the data that you would like to consider for your evaluation, and then you can choose either you can put the output in a different window or you can select a certain cell so you can have the results in that cell. When you click OK, you will have here two sets of the results. So I have the pre-treatment and I have the post-treatment result. When I run the analysis, I got the summary statistics for those data that have been provided before the treatment. It shows here the average, the standard deviation, and all the essential data summary, including the confidence level. To the right side, you will see that this data has been changed after the treatment. So here you can judge whether the data has been skewed from the normal distribution. Now that you have an overview of the summary statistics for the data in hand, you would like to go further and analyze the two different sets of the treatment. The best way to do it is to use whether t-test or ANOVA test. To do this, go to the toolbar at the top, select Data, choose one of the tests that you are interested in, and click OK. The next, you will get the pop-up menu. Here, it will take you to the next step where you will need to choose the input variables that you have. So you will select the range of the data. You will select the alpha level, which we just described as it will be 0.05, and then whether you would like to have the outcome in a new worksheet or in the same worksheet, but you need to specify the cell. And here I specified that I would like the results to be in the same data sheet. You click next. Here I have the outcome as two sets of results. The top one, it's showing me the t-test, and the bottom one, it's showing me the ANOVA test. So instead of using the software that do the statistics analysis, you can simply use Microsoft Excel if you don't have the other softwares like Stata, like SPSS, or like SAS. So you can simply use the functions that are available in Excel. Another option is to use R for statistics. One of the packages that you would like to explore is the tidyverse. It's a good tool to provide some data manipulation and visualization. For example, you can read the datasets using different format. You can plot your visual using the ggplot. You can do some filtration and you can shape your data. Now let's look at two different terms that have been used in data analytics. There is a distinct difference between correlation and causation. In statistics, the relationship between the predictor and the outcome, it could be a positive relation or a negative relation, which means that when the predictor change, the outcome tend to change. In the scenario of the breast cancer mutation, if you find that there is a correlation between the presence of the mutation and the presence of cancer in the patient, that might be related. And then you can suggest that there's a correlation between getting the gene and the development of the cancer. However, it does not necessarily imply that the mutation causes the development of the cancer. The key point here is that correlation alone does not imply causation. So two variables might be correlated due to coincidence, underlying factors, or a complex interaction where causation is not direct. Causation, on the other hand, indicates direct relationship between the cause and the effect, the predictor and the outcome. And this can be observed here in this example. When we look at the mutation in the breast cancer gene, you will see that the mutation has disrupted the function of the protein during the DNA repair, which consequently led to some accumulation of the damaged DNA, and this caused the cancer. Here, you will see that the mutation has directly caused the impaired DNA to be repaired. And here, this is a causal relationship between mutation and cancer development. There are some criteria that can play as a guideline for you to test whether this is a causal relationship. Those criteria can determine if the cause preceded the effect or this is just a correlation, not a causation. This criteria is called the health criteria, and there are 9 factors that we will look through them. The 9 criteria to validate if this is a causal relationship or a correlation will go through temporality, biological plausibility, consistency of the result, the strength of the association, the dose and response effect, the reversibility, and how you can look through some evidence. We'll take one criteria at a time. The first in the criteria is the strength of the association. You would like to look at the relationship between the predictor and the outcome. The stronger the association between the cause and the effect, the more it's likely to be a causal relationship. In the scenario of smoking and lung cancer, if the relationship between smoking and lung cancer is strong, you can imply that this is a causal relationship. However, you might consider that some people they can get lung cancer and they are not a smoker. So this will question the strength of the association. The next criteria, the association is observed consistently across different studies, across different people and different settings. An example of this is the link between smoking and lung cancer. This has been observed in different studies across different populations, and that support the consistency of the finding. The next criteria A cause leads to a specific effect. So rather than multiple effects, the more specific the association, the stronger the case for causality. An example is if the exposure to a particular substance leads to a specifically certain type of cancer, this would support a causal relationship. The next criteria is temporality. The cause must precede the effect in the time. And this is the only criteria that is absolutely essential for establishing the causality. For example, for smoking to be considered as a cause of lung cancer, the onset of smoking must occur between the development of cancer. So if you want to prove that smoking leads to cancer, so the patient they have to be smokers. The biological gradient, which we call the dose response effect, there should be a direct relationship between the dose and the exposure and the risk of the effect. So the higher the exposure, that would lead to greater risk. Let's take an example. The risk of the lung cancer would increase with the number of the cigarettes that the patient smoked per day. That would demonstrate the dose response relationship. The more they smoke packs, the more that they could get the cancer. In plausibility, there should be a biological plausible mechanism that you would like to explain by which the cause can lead the effect. For example, smoking introduces carcinogens in the lungs, which can damage the DNA and then would lead to cancer. This will provide a plausible biological mechanism. The coherence, so the observed association should be consistent with the existing knowledge and the theories about the disease and its mechanism. For example, the relationship between smoking and lung cancer should be coherent with the current understanding of the carcinogens. The next criteria can be validated through experiment. So causal relationship can be supported by some experimental evidence. If you remove the cause, the effect will not happen. Let's stick with the same scenario for smoking. If, for example, you suppose that the patients will decrease the number of smoking, so that would decrease the number of cases that they develop the lung cancer. You proved in the experiment that if you remove the cause, the effect has been reduced. The last criteria of causality is called analogy. And this means that if something similar is known to cause the certain effect, it can help support the idea that the same effect may happen in the same cases being studied. Let's stick with the same example. If we know that smoking to certain chemicals can cause lung cancer, this helps strengthen the argument that smoking that type of tobacco, which involves the exposure to similar substances, can also cause lung cancer. Now let's explore how data visualization can power your research and emphasize your results. Data visualization became the key of the current century, especially in research skills. Research show that 30 to 50% of our brain it can process visual information. Let's consider this current scenario. I have provided you with a table that has certain numbers, x and y's, predictor and outcomes, and I have provided you with four categories. You were able to provide some descriptive analysis. Now you know how your data looks like. However, you cannot tell if there are some outliers or this has been normally distributed or has been skewed. The key component for visual tools is to know what your data is saying. Make sure that you have a reference or relevant number when you compare your results. You won't show only what is important. Get to label the data, label your graph, label your axes, and have in mind that there is no right way of making visual options. It brings around what you want to infer in your decision, taking actions, or provide some knowledge. The basic principle of visual perception suggests that our brains can naturally group elements together based on their proximity, meaning that objects close to each other are perceived as part of the same group, while similarity, where items can share visual characteristics such as shape or color, they seem to belong to the same category or the same group. The current best practice for data visualization is using some data hubs, data dashboard, and open sources. Most of the peer review articles, they ask for you to provide the data sets that you have used in your article for different reasons. And now we have different and several data hubs and open sources. Dashboards are the best way to show your data. It's what we call a data storytelling. A lot of organizations and universities, including industry and education, academia, they tend to use dashboards so they can show the trend for the data that they have. A lot of the scientific research data can be shared using some of the dashboards. For example, during the COVID-19 pandemic, there were so many dashboards that shared a lot of big data that a lot of researchers were able to use and analyze the trends. Scientific research dashboard can help better visual trends. They can track the progress and manage large data sets. Open data platform are numerous that can host valuable data sets for different reasons. You would like to explore specific examples of dashboards and learn more about how to create dashboards. This is an example of one of the dashboards that has been used to show statistics for cancer in detail, showing cancer distribution by males and females, showing the major types of the cancer and how it has been trending over the age. This is another storytelling of the spread of the coronavirus during the pandemic. Providing dashboard enabled people, especially public health departments and the public, to monitor closely the spread of the virus, the cases, and how the virus has been spreading. This is a simple storytelling dashboard. In addition, there were comprehensive dashboard to show the spread of the different variant of the virus. As you can tell, data visualization is a great tool for your analysis and for your data communication. The best and common use in our research area is to visualize the data in terms of showing comparison, distribution, current trend, deviation, doing some prediction, or proving some relationship. The best strategy for effective data visualization is to decide on the infographic of the data of interest, distinguish between the different models if you would like to show some criteria. Make sure that you provide relevant metrics and use the perfect color to distinguish between your results. The best way to present your infographics is to make it simple. Use simple graphs and simple language. Make sure that the audience or the reader they can understand the terms that you have used in the visuals. Try to avoid any clutter of information and make the visual more understandable without providing any explanation. The other thing to consider is to choose the right chart for your results. So different types of data might require from you to provide different charts. For example, there's a certain way where you can use bar charts so you can compare between factors, and you can use line chart where you can look at the trend, while you can use the scatter plot to show some relationship. And be wise and smart when choosing the colors as well. Don't forget to label your graph. When it comes to using color in your visuals, less is more. So use simple and minimal color palettes as possible to express what you want to compare and what you want to show. For example, if you look at the left side, these are the standard colors that you usually use. If you can, use only one color and usually the gray color. If you would like to emphasize your variables or your elements, you can use different colors that range between the red, the black, the orange, the green, and the blue. However, you need to be very careful because sometimes colors are dangerous. You want to make sure that all people they can look at your colors and visualize them. Stay away from colors that some people cannot differentiate between. If you would like to emphasize between different elements as they are diverging, use two colors like the blue and the red and use the degrees of the colors so you can show the divergence. If you would like to show a sequential change, so you can use just one color and use different degrees of the same color. However, if you are using different categories, different treatment, for example, or different criteria, so make sure that you choose the different color according to the color of the emphasis and staying away from the colors that are tricky to identify. In this example, I have provided you with only one color. I would like you to tell me which inner square has the darker color. If you look closer, I have bordered the four inner squares so I can make you focus on the image. You see that the four squares have the exact same color, which tell you that the background has played an effect with your visual perception. So make sure that you provide a consistent background when you want to show some differences. So it's important here to use a good background, and it's recommended to use a white space in the background so you can emphasize on your visuals. Make sure that you test and iterate what you provide. You might use the help of your colleagues so you can get feedback and improve your visuals before you put it in your paper or you present it in your presentation. The main purpose of using your visual is either to process some information or to make decisions or to tell a story. As we discussed earlier, the common use in our research is to provide some comparison. You compare between items, so you can use some sort of bar chart or you can use some trend. You can also show the component of the elements that you are presenting, in which you can provide like a bar chart or a pie chart. And then you can also emphasize on relationship, which you can use some bubble chart and you can use a trend line. In presenting your visual, make sure that you already highlighted and revealed the pattern that you observed in your results, showing some trends going up or down, increasing, decreasing, or no change. if there is any fluctuation, if there is some gap, or if there is any screwness, that would be your interest that you would like to show in the result. Another key here that you can play with to highlight and emphasize the pattern and the trend is to play around with the length of the bar, the width of the bar, the size of the bubbles, or the intensity of the dots. The last piece of your data analytics in data visualization is choosing the best chart for your result. A histogram will be your best option to display distribution of your data sets. In here, you can group your data into bins and show the frequency of the data points. Another option is to choose a scatter plot. In here, you can show a relationship between two continuous variables by displaying the data points. And there's a whisker plot, or we call it the box and whisker plot. This summarizes the data set's distribution by showing the median, the quartiles, and the outliers. Another scenario is using a line chart, which is best used for visual data when you aim to show the trends over the time. A step chart, in this case, you can present your data with a series of steps, and this will highlight the sudden change or the period of stability in the data. This is very useful if you would like to illustrate in discrete shifts rather than just the gradual trends. The bar chart is used to compare different categories. The column chart is ideal to compare the discrete items over the set of time. The stacked colon is best used for showing the cumulative total across the categories. And one more is the clustered. This one is useful for comparing multiple data series side by side. If you look here at the difference between the bar chart and the line chart, so the bar chart to the left, you cannot really notice the difference in the pattern. The line trend tracks the change over the time. The trend line, this is used for the data visualization, and it can look at the pattern, it highlights the trend, and it gets the attention to where you want to emphasize the shift. If you look here at the line chart, comparing between the image to the right to the image to the left, if you just use the image to the right, this lacks the detail and the information of the shifts in between. If your research interest is to look at the gradual change in the shift, so you better use the detailed track of the data showing at each small interval. Another option is to use the bubble chart. This is used to display the three dimension of the data, where the size of each bubble represents the magnitude of the third variable, making it very effective for your visual correlation and distribution. Another option is to use the heat grid or the heat map, and this has been frequently used with different color intensity to represent the data values across two dimensions, making it useful to identify patterns of the correlation and the outliers. When it comes to using the line chart is ideal for tracking changes over time by connecting the individual data point with continuous line, while the area under that it tells you what's beneath and it emphasizes on the volume of the change. However, there is a stacked area chart that builds on this by layering multiple data sets on the top of one another, and this show how each contributes to the total overall time. If your data requires some prediction, when you want to see what to expect in the future, for example, or how the data would behave, this is where you can use the projected forecast or the prediction chart. This is based on structured, informed data that you feed to your program, and then consequently, there will be some sort of algorithm that will predict the behavior or the trend of the line. Another way is what we called the spaghetti chart, and this compares between different intensity and different categories. However, in certain instances, it's very difficult to use the spaghetti chart because you cannot emphasize on the importance of each line. In this case, you would rather consider breaking them down into single lines so you can observe each single pattern individually. The last two visuals we will consider for this session is the raster map informatics, which is a kind of visualization that uses some pixel-based data to represent some spatial information with some varying intensity, while the radar chart, it's used to display multivariate data on a circular grid, showing how each variable compares across different categories. If you notice, those two charts are commonly used in imaging and in looking at the intensity of radiation absorbed in a certain organ. To summarize what we have learned during this session, let's emphasize on the key objectives takeaways. We have learned that data analysis in molecular biophysics provide a deep insight into some description of mechanism and underlying various diseases, and this will enable in identifying some novel elements such as the biomarkers in developing some tools for your research to detect some diseases at earlier stages or to improve the outcome in a timely manner. You have also learned that data-driven approach plays a major role in molecular sciences, allowing for better development of treatment, allowing to consider different factors such as genetic and environmental factors, and this would enhance the efficacy of using some therapies and treatment where they can minimize the side effect as well as can be more precise and effective. With a high demand in finding better treatments and more options for patients, the integration of big data and the advanced analytic tools would accelerate development of more discovery options. By analyzing those big data sets from different data sources, including the genomic data sources, that would enable identify better and potential targets that would be quickly and effectively and can lead to solutions for puzzled agents. Overall, experienced researchers demonstrate dedication to the techniques, employ detective skills to make connections, excel in the data storytelling, as well as working with data to find patterns and effectively present their findings. Some helpful tools that you can benefit from when you come to your data visualization. You can use Microsoft Excel. You can use Google Data Studio, Power BI, or Tableau. Those are good tools to present your visuals. As well, you can use R and Python. You can use some statistical packages such as SPSS and SAS. R and Python might be a free option. However, SPSS and SAS, they need some license. Real-time data visualization can benefit from using Power BI. As well, you can use some Canvas to provide some better visualization. And for the dashboard, the best way to use the tools is Tableau or Power BI. One of the tools we just discussed is SAS. SAS is a very good and helpful source if you would like to analyze your data, visualize your data, and then use the dashboard. SAS is providing an option as free on the cloud if you are eligible and you belong to some of the academic institutions. If you are not a data savvy and you would like to skip through the details of the analysis, it might be helpful to use some built-in resources that is already designed for you to export your data and then look at the trends and how the data will be analyzed. One of those sources, which is very helpful, is designed by John Hopkins and is called the OpenAPI. This is another helpful open source where you can look at the power of the study. If you would like to learn more about effective data visualization tools, how to choose the chart that is appropriate for your data, or if you are interested for your own leisure time to learn about how AI was used to recognize facial expressions, and it has been developed as one of the big projects nowadays, I would recommend those three readings. At the end of this session, it was a great pleasure that you give me the opportunity to share with you some of the data insights and data visualization. For any future references, or if you would like more information, please don't hesitate to contact me. I have provided my email. Thank you again and have a great day.